In this week's video, we're going to be covering Chapter 2 on probability distributions. In last week's video, we focused on discrete distributions and continuous distributions. Today, we will continue with Poisson process and Monte Carlo simulation. So let's begin. We start by understanding what a Poisson process is. A Poisson process is essentially a counting process which counts how many events occur over time. For example, think of real-life situations like the number of calls arriving at a call center, the number of customers entering in a shop, or the number of accidents on a road. In all these cases, events happen randomly over time, and we can count how many have occurred. Now, since Poisson process is essentially a counting process, it's obvious that it will follow all the characteristics of a counting process. Let's discuss these one by one. Let's start by taking a variable t, which represents a particular time period. Then, n of t will represent the number of events that have occurred in the time period t. The first characteristic of a counting process is n of 0 is equal to 0. This means that at time 0, no time has passed, so naturally, no events could have occurred. This is the starting point of the process. Second, for any t that is greater than 0, the number of events in t is integer valued. Since we are counting events, the value can be 0, 1, 2, and so on. It can't be fractional like 2.5 events. Third, if s is less than t, then the number of events occurred in time period s will be either less than or equal to the number of events occurred in time period t. As time increases, the number of events can only stay the same or increase. It can never decrease because events have already occurred and cannot unoccur. Fourth, the number of events in time t minus the number of events in time s is the number of events in this range. This tells us how many events have occurred specifically between the time s and the time t. So instead of counting from start, we can isolate the events in any interval. Now that we've discussed all important conditions of a counting process, let's further discuss the additional conditions which make it a Poisson process. Before we understand these, it's important to get acquainted to a few new variables. Here we have h, lambda, lambda times h, and O of h. Let's understand what these mean. Let's start with lambda. Lambda is the rate parameter, meaning the average number of events that have occurred per unit of time is represented by it. It tells us how frequently events happen. For example, if lambda is 5 per hour, it means that on an average, 5 events occur every hour. H is a very small time interval. We consider the small time interval t and t plus h. Then we have lambda multiplied by h, which gives us lambda times h. This represents the approximate probability of exactly one event occurring in the time h. Since lambda is events per unit of time, multiplying it by a very small time interval h gives us the chance of one event in that interval. Then we have O of h. This represents a term that becomes negligible compared to h as h tends to 0. This means that such a term vanishes faster than h, so practically we treat it as negligible. First, we have the behavior of the Poisson process in a very small interval. We consider what happens in a very small time interval of t plus h. given that the number of events in T is equal to R. We start with the first subpart, the probability that n of T plus h equals R, given that n of T equals R is 1 minus lambda h plus O of h. This means that if there are already R events at time t, then the probability that no new event occurs in a small interval t plus h, that is, the number of events in t plus h remains R, is 1 minus lambda h plus OH. So the probability that no event happens is a probability that is close to 1. Then the small chance of one event is captured by lambda h. And at last, O of h adjusts for very tiny effects. The second subpart is the probability that n of t plus h is equal to R plus 1, given that the number of events in t is equal to R is lambda times h plus O of h. This means that if there are R events at a time t, then the probability of exactly one new event occurring in a small interval is proportional to h and approximately lambda h. The probability that exactly one event happens is represented by lambda h, and O of h is again a very small correction. The third subpart is the probability that n of t plus h is greater than R plus 1, given that the number of events occur in the time period t is R, is O of h. This means that the probability of one or more events occurring in such a tiny interval is extremely small and negligible. So, the probability of two or more events occurring in a tiny interval is almost impossible. That is why we ignore this case in most calculations. Let's move on to the second condition. This states that events that occur in non-overlapping time intervals are independent. What happens after the time s does not depend on what happened before the time period s. The number of events in this range of s to t is independent of the number of events before s. So, the process has no memory of past counts when considering future intervals. If the above conditions of a counting process followed by these additional conditions of a Poisson process are followed, then the number of events by time t follows a Poisson distribution with the parameter lambda times t. The probability that n of t equals to n is equal to e to the power lambda t into lambda t to the power n divided by n factorial. Now we study the derivation of the Poisson process for the number of events that occur up to the time t. We start by defining our function p of t with the subscript n equal to the probability that n of t equals n. This means that this function denotes the probability that exactly n events have occurred by the time t. This equation here represents an example of the concept covered. This means that it gives the probability that exactly 3 events occur during the first 5 units of time. Now, our goal is to find the exact formula for this function. To do this, we study what happens during a very small extra time interval, t to t plus h. Here, t is the current time period and h is a very small interval, so we move from this to this time period. To do this, we begin with our first case, where n is greater than or equal to 1. We first handle the case where the number of events is at least 1, because this allows 2 possible ways to reach n. To have n events by time t plus h, we have exactly two possibilities. The first condition being that n-1 events already exist by the time period t and one event occurs in this interval. And the second one being that n events have already been established by time t and no event occurs in this interval. Now we convert this logic into probability form. We now represent the probability of n events occurring in the time interval t plus h using the following equation. This is the sum of the first two cases that we'd covered earlier. The first case is written as the probability that the number of events that occur in the time period t is given by n-1 multiplied by the probability of one event occurring in this time interval, given that the number of events in time t was n-1. This is added to the second case, wherein the probability of the number of events occurring in the time interval t is given as n, and no events occur in this time interval, given that the number of events in t is equal to n. Using the Poisson process assumptions covered earlier, we can write down each of these two cases as these equations and add them. Without making this process too lengthy, if we first expand the equation and then subtract the probability of t events with the subscript n from both sides, we obtain. It's important to expand this equation in order to solve it properly. Thereafter, we subtract p of t with the subscript n because we want to prepare the equation for differentiation. We take the equation which we've obtained and divide it by h. Now let h tend to 0. Using the definition of derivative on the left hand side of the equation, we obtain. This gives us d by dt of p of t with the subscript n on the LHS. We also know that the limit of h tends to 0, O of h upon h is equal to 0. So now when we take this equation, we substitute the LHS with this value and we put 0 over here. This gives us This is called a differential difference equation and tells us how probability changes over time. This marks the end of case 1. We now move on to case 2 of the derivation. In this case, we study n is equal to 0. This case is important because when there are 0 events, the process behaves slightly differently. To derive the probability equation for this case, we again look at a very small time interval. Here, we want the probability that there are 0 events up to the time period t plus h. That means that there must already be 0 events up to the time t, and no new event should occur in the small interval t, t plus h. Unlike case 1, there is only one possibility here. So, only one path exists. We can write this mathematically using the following conditional probability. The probability of the number of events that occur in the time period t plus h is equal to 0 is the probability that the number of events that occur in the time period t is equal to 0 multiplied by the probability that 0 events occur in the time interval given that the number of events in t is equal to 0. Then, using the Poisson process assumptions, we can write this mathematically as p of t plus h with the subscript 0 is equal to p of t with the subscript 0 multiplied by 1 minus lambda h plus O of h, where this function represents the probability of 0 events up to the time t. 1 minus lambda h is the probability that no event occurs in the tiny interval, and OH is a very small higher order term. We rearrange this by expanding the right hand side and subtracting p of t with the subscript 0 from both the sides. This gives us. We now divide this equation by h. After that, we take the limit h tends to 0. Using the definition of the derivative on this equation, we obtain d by dt of p of t with the subscript 0 is equal to minus lambda into p of t with the subscript 0. Let's conclude the findings of case 1 and case 2 to derive the formula. We know that at the time 0, no events have occurred yet. So, p of 0 with the subscript 0 is equal to 1. Also, p of 0 with the subscript n is equal to 0 for n is greater than equal to 1. This is because it's impossible to already have events in the starting instant. Therefore, after solving both of these cases, we obtain probability of the number of events occurred in the time interval t is equal to n is represented by e to the power minus lambda t multiplied by lambda t to the power n upon n factorial. This can also be represented as n of t follows Poisson distribution with the parameter lambda t. So, the number of events occurring up to the time t follows a Poisson distribution with the mean lambda times t. The main idea of case 1 and case 2 is that they help us understand how the probability changes over a tiny interval of time. Case 2 first finds the probability of getting 0 events over time, which naturally produces the exponential term e to the power minus lambda t. Then case 1 builds a relationship between the probability of getting n events and the probability of getting one fewer event. Solving these relationships repeatedly creates the pattern of multiplying lambda t again and again and dividing by the factorial of the terms. That is how the full Poisson formula is gradually obtained. This derivation is important because it shows us how the Poisson distribution formula is mathematically obtained from the assumptions of the Poisson process. Let's understand the waiting time between events, also known as the waiting process. We start by taking t1 as the waiting time until the first event occurs. Now, instead of counting the number of events, we shift to measuring the time between events. If t1 is greater than t, this means that no event has occurred up to the time t. Therefore, the number of events observed up to time t is 0. So, t1 is greater than t if and only if the number of events occurred in the time period t is 0. This means that both the statements are equivalent. Now, since n of t or the number of events in t follows a Poisson distribution with the parameter lambda times t, we can conclude that the probability that the number of events in t is equal to 0 is given by e to the power minus lambda t. This is because the probability that n of t is equal to 0 is given by e to the power minus lambda t times lambda t to the power 0 upon 0 factorial according to the PDF of the Poisson distribution. Now, to find the CDF. We know that the CDF is equal to the probability of t1 less than or equal to t. Using the complement rule, this gives us 1 minus the probability of t1 greater than t. In the previous equation, we had already found out this value as e to the power minus lambda t. So we substitute this here to get the CDF as 1 minus e to the power minus lambda t. Hence, t1 follows an exponential distribution with the parameter lambda. Now, let t2 be the time period between the first and the second event. It's important to note that this is the time period between the first and the second event and not the time period up to the second event. In a Poisson process, events occur independently over time. This means that after the first event occurs, the process starts afresh. So what happens next does not depend on what's happened before. The waiting time after the first event has the same distribution as the first waiting time. Therefore, t2 also follows an exponential distribution with the parameter lambda. Similarly, this continues for t3, t4, and so on. Thus, the inter-arrival times in a Poisson process are independent and identically distributed random variables. This property is called the memoryless property. In simple words, after each event occurs, the process effectively restarts and the waiting time for the next event behaves exactly like a fresh exponential random variable. Now, let's cover the last topic for today's video, Monte Carlo simulation. Monte Carlo simulation is used when a probability distribution is given to generate random variables using random numbers, usually from u 0, 1. So what this means is, many probability distributions are theoretical. Monte Carlo simulation helps us generate sample values from those distributions using a computer or random numbers. The basic idea is, we first generate a random number between 0 and 1. Then we transform that number into a value from the required distribution. For example, instead of only studying exponential distribution theoretically, Monte Carlo simulation allows us to actually generate exponential random values. Let's understand how this is done for continuous distributions first. There are two methods which can be followed. The first method is where f inverse of u can be found. And since the inverse can be found, this is known as the inverse transform method. And the second method is where f inverse u can't be found. Let's start with the first method under continuous distributions. This is based on the premise that f inverse u can be found. What this means is if we can find the CDF known as the cumulative distribution function and solve it algebraically, then the simulation becomes easy. So we start by generating a random number u from u 0, 1. This gives us a uniform random value between 0 and 1. Then we use the CDF given by u is equal to f of x. And we solve the equation for x. We rearrange the equation to obtain the simulated value. Thus, we obtain a random value. Let's understand this properly with the help of an example. So the question asks us to generate the random value from an exponential distribution with lambda equal to 2. As covered in part 1 of the 2-part video series on this chapter, the CDF for an exponential distribution is given by 1 minus e to the power minus lambda x. Let the random number be 0.7 since it lies between 0 and 1. We use the inverse transform method where we equate u with f of x. This gives us x is equal to minus log of 0.3 upon 2. This is approximately 0.602. Therefore, the simulated exponential value is 0.602. Oftentimes, instead of taking our own random value, as we have here, the question will already provide one, and we're supposed to substitute it to directly find the value of x. Let's move on to type 2, wherein f inverse of u can't be found. If we can't solve u equals f of x, we use either tables or approximation. To solve such questions, we first generate a random number u between 0 and 1, where every value is equally likely. Then we find the value of x such that the cumulative probability is equal to u. Since the inverse can't be found directly for normal distribution, we use statistical tables or normal approximations. Let's understand this with the help of an example. The question says, simulate a random value from the standard normal distribution when u is equal to 0.975. So we start by generating a random value u which follows u of 0, 1. Here we have already been given u is equal to 0.975. Now we find the value x such that the probability that x is less than or equal to x is equal to 0.975. Since the inverse of the normal distribution cannot be solved directly, we use the standard normal table. From the z table, it can be observed that x is equal to 1.96. These are the two important methods used to simulate continuous probability distributions in Monte Carlo simulation. Now, let's understand how random values from discrete probability distributions can be generated using the Monte Carlo simulation. We start by considering a discrete random variable x with known probabilities. Then we generate a random number u such that its values lie between 0 and 1. After that, we find xj such that the random value u which was generated earlier lies between f of xj minus 1 and f of xj. Then we assign our random variable x equal to xj. Let's understand this with an example. The question says, suppose a discrete random variable x has the following probability distribution. The probability that x is equal to 0 is 0.2. The probability that x is equal to 1 is 0.5, and the probability that x is equal to 2 is 0.3. Simulate a random value when u is equal to 0.65. So the first step is to generate u. Since that's already done for us in the question, we move on to the next step. We start by constructing the CDF. F of 0 includes all values up till 0. F of 1 includes all values up till 1. So here we'll add 0.2 and 0.5. This gives us 0.7. And at F2 we follow the same procedure to get 1. Now we compare the random number with the cumulative intervals. The random number is 0.65, which lies between 0.2 and 0.7. Since 0.65 lies within this interval, it means that we assign x is equal to 1. We find xj such that the random value lies between f of xj minus 1 and f of xj. Here, f of xj is represented by 0.7. Therefore, according to the steps we'd studied earlier, we set x equal to xj. Since f of 1 gives us 0.7, therefore the value of xj here is 1. This gives us x is equal to 1. Let's take another case where the random value to be simulated is 0.7. Since we've studied in the rules that the condition is less than equal to, we can repeat the same equation we did in the first part for the second part, changing the value of u, and we would still get x is equal to 1. That brings us to the end of this video on probability distributions. I'll be back next week on Actuarial Simplified with Chapter 3 on generating functions. See you next week.